Well, good morning, Haskell Exchange. This is exciting. This is one of my favorite meetings of the year, and it seems to come around more and more often. Now, I'm convinced one's perception of time is logarithmic. It takes the same subjective time to double your age. And since I probably am double the age of some of you in the room, your perception of time is going twice as slowly as me. However, this talk is going to go quite quickly. Got quite a lot to say. Please do ask questions as we go. Right, I will repeat the questions so that you don't necessarily need a microphone, but sort of speak clearly and ask. Because I'm going to show you lots of code because that's always more fun. And I would like you to understand, right? So we will somehow get to the end of the talk anyway, even if you ask questions. All right. Here we are. This is what the life of a researcher should be like, right? You have a problem that looks really tricky. You think about it, and you figure out a way in which it is easy, right? So all of your friends are terribly impressed with your work, but nevertheless, it only took you 20 minutes. This talk is about a much less good plan, right? Which is to have something that looks easy, and then you think about it a lot, and it turns out to be really hard. So that's why it's actually taken quite a while to get here. So this talk is written, these two, I'll say a little bit more, Ryan Scott and Sebastian Graf had quite a lot of hand in this talk, as you shall see. So they're part of this, the process of getting back to this, okay? So that's to sort of set the scene. So let's do the easy bit first. Here's the famous isJust function. So what's going on here? Well, you just want to say, does it cover all the cases? This is a find function. A value of type maybe A can be nothing, or it can be just something, and the function covers both. Now what have I done? The function covers both possibilities. There's one for just and one for nothing. Fine. So far so good. What about this one? Not so good, because you've missed out the case for just. And if you've got a lot of patterns, big data types, and you've changed them a lot, then it's really helpful to know when some are missed out. So, and if you run it, you'd rather not have this happen when you're running in production, right, for your clients. You don't really want them to see messages like this if you run isJust. So we'd like the compiler to produce a warning, and GHC indeed does, that says, look, you've missed out an equation for isJust. The just pattern is missing. So you'll have all seen this, okay? So far so good? Okay, so we want to report two things. One is equations that are missing altogether, like the one I've just shown you. But another one is equations that are just redundant. Right? This one here isn't doing anything, right? Because the case is already covered by this guy. So this equation isn't wrong, it's just not helpful. Right? So we'd like to report that to the user and have them delete it. Especially if the right-hand side is different, right? So then they're going to get confused about which one is running. Okay? So far so good? Okay, now, you would think that this was easy, right? So, in fact, look here, see, look, this is the problem that looks easy. How hard can this really be? Currently, and this is after 30 years of development, right? We have over 80 tickets about pattern match warning failures, and 24 of them are still open. So what is going on? What is happening? So I'm going to show you. So, first thing, I'm going to show you a series of things that make pattern matching a bit less obvious than you might suppose, and then I'm going to show you that way lies madness, and I'm going to show you how to get rid of the madness and get back to a nice simple world. And I hope you'll emerge from this talk with a clear understanding of how to deal with the complexities of pattern match warnings, which by then I hope you will be viscerally aware of in a very simple way. So, here's complexity number one. Well, what about functions with multiple arguments? So here's a function that's if you look at the pattern matching literature, and there's quite a big published literature about it, here's a famous function written by a chap called Girard Berry. Here it is. Are there any missing equations here? Have a think. What do you think? Any missing equations? Oh, yes, somebody. What was that? I can't hear you. Triple false. The triple false is missing. Absolutely. Very good. That was quite impressively fast, actually. Right, so triple false and triple true, I think, is also missing. But it takes a little bit of puzzling to work this out. And moreover, you might imagine here there are, if you were to work out, one way to work it out is to think of all the combinations, right? How many combinations are there? 8, 2 to the n, right? So if you get lots of patterns, you have lots of combinations, perhaps an exponential number of combinations, and it's clearly a bit painful to work through an exponential number of combinations in thinking about what patterns are there and what are not. And so, in fact, this question is worst case exponential anyway, as it turns out. But what we want to do is to make the compiler do a good job of dealing with the easy cases fast, and maybe trying to avoid falling into an exponential case, unless it's absolutely necessary, and even then, not waiting for the lifetime of the universe. So let's see. So yes, so it's a little bit hard for people. Now, what about, so that's about multiple arguments. That's the first little piece of complexity. You can see that there's the interactions a little tricky to work out. But what about this one? Is the second equation redundant? First of all, why might you think that it was redundant? That is, deleting the second equation would make no difference to the program. Why might you think that would be true? Because somebody said loudly? Because the first equation deals with the false case in the second argument, right? And the second equation seems like a special case of the first one, doesn't it? Aha. So, well, you might say, silly programmer, you should have written the second one first, but supposing this is the program, right? So you would think anything that matches the second equation will have matched the first, and so the second is redundant. Why is that not true? Bottom. Yes, the answer to all questions in Haskell is bottom, right? So if you call this function applied to, well, let's say a call to error and true, what will happen on the first equation? It won't match, because the first equation has the second argument is false, right? So second argument is false, so this true will mean it doesn't match. So then we'll get to the second equation, which will try to match the first argument against true, which will fail, right? So if I delete the second equation, the behavior of the program would change. Programmers hate it if compilers change the behavior of your program. So deleting the second equation, not a good plan, okay? But I hope you will agree, we're only in 5 minutes into the talk, I hope you will agree this is not obvious. All right? There's a little bit of trickiness going on here. All right? Let's see. Interestingly, we can never actually return 2. Because, why because? You would diverge first, right? The second equation is never going to succeed in matching and get to the right-hand side. It's going to try to match that first argument and diverge or report error of Irk. Okay? So this is weird. It's an equation that is not redundant, but neither can you get to its right-hand side. A little scary, don't you think? So GHC these days will say this. It will say the right-hand side is inaccessible. And that's what this means. You can't get to the right-hand side. But with the other one, it would say it's redundant. But with this one, it just says it's an inaccessible right-hand side. You could write whatever you like there. Nothing is ever going to happen on that right-hand side. A little strange, don't you think? All right? Having fun yet? Now, what about bang patterns? Right? More bottoms are going to be coming. So here is a data type called void that has no data constructors. GHC lets you do this these days. I think you have to say empty data types as a language extension. Void has no constructors. So what values of type void can you construct? Only one, namely bottom. That's right. The right answer in this talk is always bottom. And so here is a way in which you can construct a value of type void. You could call h on 3, right? H of x is h of x, so it is indeed bottom. Or error of Irk is also has type void. So it's a funny type. It only has a single inhabitant, bottom. Now, so much for, OK, so these two calls here to G1 and G2, these are both well-typed calls. They construct a bottom value of type void and pass it to f, which then ignores it and returns true. So far, so good? OK, so now what happens with this kind of data type? So here's S maybe stands for strict maybe here. S nothing and S just of bang. Look at that bang, right? That says the SJust constructor is strict in its argument. It evaluates its argument before it'll return an SJust box. Okay? This is good. People often use these strict data types because they let you build more space-efficient structures that don't have space leaks and thunks lying around in them. Okay? But now, what happens here? What is this equation redundant? All right, hands up for yes. Redundant, you can delete it. Hands up for no. Ah, see, right, pretty good. But roughly equally split. GHC thinks yes, it's redundant. Why? Well, because how could I construct, SJust, remember, the type of the function is S may be a void. So this argument here must be of type void, which means it must be bottom. But when I construct an SJust up here, right, I evaluate that bottom. So I cannot construct the value SJust bottom. If I try to apply SJust to, say, H of 3, SJust of H of 3 will evaluate the H of 3, which will produce bottom, right? So what that means is there are no values other than bottom that look like SJust of something. Well, bottom doesn't look like, there are no values that are SJust of something. It's an uninhabited, part of the data type. So in fact, the only thing that can happen is either the argument to f can either be S nothing, or it can be bottom, but nothing else. So if I delete the second equation, if I give it S nothing, I get into the right-hand side, I return 1. If the argument was bottom, what would happen? What happens when I match S nothing against bottom?
You bottom out.
Divergence, right? So matching is always strict. So this pattern match right here in the first equation, if I give bottom, or error of ERK, to F, F will say, let me evaluate you to see if you're S nothing, and that will diverge, if it's in fact one of these SJust things. Okay? So yes, the second equation is redundant. The people who said, no, it's not redundant, are you satisfied? You can ask questions, or, I mean, this is not obvious, right, this stuff. But this is what compilers are supposed to do, is to fix all cases. Okay? All right. Let's see. Yes, so, right, second equation redundant. Said that. Good. You can delete it. Now, here is a slightly different example in which I haven't put the bang in the data type. This is ordinary old maybe now. Now I put the bang in the pattern. So we have bang patterns these days. Another extension. So now what? Now, maybe void, that data type, that type, now does have inhabitants nothing, just bottom, and in fact bottom as well, are all inhabitants of this type. When I say inhabitants of a type, I mean what values have that type. So unlike S maybe, right, I couldn't have S just the bottom because the S just was strict, but I can have just the bottom. So now what happens here? Well, if I give F just bottom, it won't match the first. Will it match the second? What will happen if I match against the second? What does bang patterns mean? They mean during pattern matching, be strict. Evaluate this component, right? So what will happen when I match just bottom against this second pattern? Diverge, right? Remember, the answer is always bottom, divergence, some variant of that. So yes, when I try to match, when I try to match this bottom against that bang pattern, boom. So this is another example of an equation that is not redundant, but if I deleted this equation and gave F just bottom, it would not match this and fall out, into, well, thin air, right? That's incomplete patterns, right? So this is not redundant, and nevertheless, again, I cannot get to the right-hand side, so it's an inaccessible one of those guys, okay? Somebody ask a question or make a comment? You're looking a bit passive at the moment. And I can see you. Yes, at the back. Does the compiler know that you can never get to that too, and perhaps avoid generating code for it? No, in fact, I mean, it could, because it's going to report a warning, right? But in fact, then we generate code for it anyway because you're probably going to fix it in some other way. If you are told that it's inaccessible, you're probably going to do something like return 6 or case X of bottom or just error, something small. But yes, it will never be reached. If it happened a lot, I suppose we could maybe save a bit of code. Anyone else? Yeah, sorry, yeah.
What are typical applications of bottom? Because I always skipped it when I read about bottom.
Oh, what are typical applications of bottom? Oh, man. Bottom is, you mean, why would you even want a data type like this, for example? Okay, so let's be concrete, right? Applications of bottom is too general. Okay. Why would you ever want void? Well, sometimes you have a data type that's parameterized over something, like, say, list of A. What would list of void mean? Well, that would be like saying it's sort of list-shaped, but I'm really not interested in the elements. So sometimes you have a data structure that is parameterized, but it turns out you're not interested in the element type. So then list of void might be a sensible type in a particular application, and it would mean you could use all the listy functions. Does that make sense? Yeah.
I will take a look at.
Yeah. So bottoms are very yes. Okay. Anyone? Yeah. Anyone else? Yes. Oh, can you define the phrase will diverge? So it might mean evaluating this expression will go into an infinite loop. It might be that GHC at runtime is clever enough to spot that it's in an infinite loop and will print angle brackets, loop, angle brackets, angle brackets. Or it might mean something like these calls to error. Where did I have a call to error? Here. This guy, what error has type for all A, string arrow A, right? That means you give me any type A and a string, and I'll cough up a value of type A. Well, obviously, that's a bit difficult, right, for any type, but the way it does it is by saying, I'll just go into an infinite loop. But that's rather, to actually go into an infinite loop would be rather unhelpful. So what it actually does is it says, guys, you called error, right? Or more precisely, it throws an exception, which you can catch in the IO monad. Okay? Okay, let's keep going. Right, guards. Another piece of pattern matching complexity we have to take account of. Here's a program that computes the sort of sign or some variant of the sign of x. If it's smaller than 0, this. If it's equal to 0. Now, is this, let's see, are these equations exhaustive? Are there any missing? Bottom is not the right answer. For a change, it is not the right answer. No, these equations are, in fact, exhaustive. Right? One way to see they're exhaustive was otherwise. Now, what's otherwise? So actually, it's merely an ordinary value. It's not a keyword. It's simply an ordinary value that's defined in the prelude to be true. So in order to see that this is exhaustive, I've got to be able to see the value of otherwise, which is a bit more than we've talked about before, and to see that these two cases are not, is this redundant? Right? If it was less than or equal to 0 in the first guard, right, then the second equation would have been redundant, but that involves reasoning about less than and equal. So clearly, in general, once you get guards involved, you're going to get something you cannot figure out completely at compile time. But that's okay, we'll just do a best effort. What you might hope is that the compiler is going to do a reasonable job of such things. Here's another example. This is a pattern guard, yet another GHC extension. So what does this mean? This means, let's just double check that is everybody just to double check happy with this syntax? This means sign of x, where x is less than 0, return LT, where x is equal to 0, return this, or where otherwise, return. So these are the three alternatives. So here, this says last of x's where, oh, and this is a pattern match. This says call reverse of x's and pattern match the result against y cons blah. If that pattern match succeeds, return the right-hand side. Otherwise, fall through into the next guard, the next vertical bar thing. Does that make sense? Is that okay? Pattern guards, maybe you haven't all seen pattern guards. They're terribly useful. If you haven't seen them, this is your introduction. Fantastically helpful things. I use them a lot. Okay, now, let's see. Is this exhaustive? Yes, because we got the otherwise case at the bottom. But it's a little bit less obvious if I did this. So now I've got two pattern guards, both of which are calling reverse. So you might worry about whether reverse is going to be called twice, but you also might worry about whether you can see this is exhaustive. We know it's exhaustive because reverse returns either cons or empty list, right? One way or the other. But you might hope that in a case like this we would spot it. But you can see there's a bit of a dial here about how clever you might hope to be. Okay? What's next? You might mix the two. Everything interacts in this space. You might do an ordinary pattern matching combined with a pattern guard. This means the same as the other is just thing, or very like the other is just thing, right? Huh. And we like to do a good job on that too. Right? Otherwise, you guys are going to write to me to say your compiler is not clever enough to do something completely obvious to the meanest intelligence. Okay? Okay, view patterns, another feature of view. How many people actually use view patterns as a matter of interest? Oh, quite a lot. Good, right. So I always wonder, I always want GHC to have telemetry. So every time you use a feature, it sends email to me or to, at least a UDP packet to home base, just so I know how much. Anyway, so I haven't done that yet. Anybody who's good at telemetry, I'd love to do that. So this says a view pattern has the form expression arrow pattern, and to match against that pattern, to match a value against the pattern, you apply the expression, which should be a function, to the value and match the result of that call against the pattern. So here, to match last against an argument, you apply reverse to the argument and match the pattern here, y cons y's, y cons something, against the. So it's very like the previous example, really. But it's yet another piece of technology that we would like our pattern match overlap checker to work. Yes? Will the reverse be called twice? So, well, you shouldn't really care because, hey, it's just functional programming. But no, GHC will go to some effort to not call reverse twice. But if you said I reverse and idea reverse, you disguised a little bit, then I'm sorry, you're on your own, right? So you've got to make it pretty obvious. But then, in fact, we will try hard. I wish I could give you, it would be a good exercise to try to give precise rules for what is duplicated, because otherwise you feel uncertain, and that's not, then you end up programming around it, if it's expensive. Sometimes these functions are very cheap, these little view functions, in which case you don't worry. Quite often they are. Last piece of complication, no, not the last piece, nearly the last piece, long distance information. Have a look at this program. What is this doing? Well, I've got a function that matches some fairly big data type here, grades, oh dear, it's not so good, A, B, and C, D, blah, blah, blah. It matches A here, and then it has a sort of fall-through case, and somewhere deep inside the right-hand side, we match on G again. Okay? Is A missing? No. We've dealt with the A case up here, right? Of course, any decent compiler should not complain about a missing thing in this case. All right? Yeah. Oh, unless ... redefines G. Let G equal 7. Yes, yes, that would be bad, right? So it's not just because it's called G. It better be the same G. Yes. So there's some kind of long-distance stuff involved in pattern matching as well. Okay. So I hope you're having fun, right? There's a lot of these features that interact with each other. And I haven't yet told you, or haven't yet reminded you, about GADTs, right? And that makes things a lot more fun. Look at this. So here is a GADT, which has two constructors. It's a little bit strange because this guy only has values of type tint and tbool, one constructed with this tint constructor and one constructed with this tbool constructor. Now, so if I know that f takes, it has a type signature. Oh, by the way, did I mention? Do you remember even earlier when we were talking about bang patterns? My reasoning that said this function is, the last equation is redundant, was based on the type signature of the function. I should have mentioned that. So there's another piece of interaction which is between the function pattern matching itself and the type signature for the function, which is another piece of sort of slightly more long-distance information you might imagine. So here is another one that interacts with the type signature. The argument is of type tint. Okay? And we pattern match on this tint data constructor. That's good. Are any equations missing? Bottom. You have to, so it has become too easy. You're going to have to nuance your answer a bit more to explain the way in which bottom is the correct answer. And anyway, is any equation missing is a yes-no question. No equations are missing, because what values of type t bool are there? Or well, rather, what values of type t int are there? We can have bottom, of course, but we cannot construct a value of type t int by calling t bool. Look, with t bool here returns a t of bool. And that doesn't, that just would be ill-typed if I called it, right? So I cannot call this function giving it a value that's constructed with t bool, right? So it can only be constructed to t int, but it could be bottom, so yes. But if it's bottom, what will happen to this equation? Diverge. It'll diverge, right? So that's good. No equations are missing, right? We don't have to add a t bool equation. Very good. Now, so we better think about that. Now, there's a long-distance version of this. Yes, yes? Where does the uppercase I? Oh, what is this? That is PowerPoint correcting lowercase capital letters to uppercase, which fortunately Emacs does not do. This is a little I. Thank you. I think it's the first person singular. PowerPoint hasn't figured out when I'm typing code yet. Okay. So there's some long-distance stuff too, right? Here's a function that takes a TA and another TA and matches on the first, and then somewhere deep inside matches on the second. So now this is unlike the last long-distance thing here, where I matched on G, and then I matched on G again, right? Here, I'm not matching on the same thing again. I'm matching on this guy first, and then I'm matching on a completely different argument, okay, inside here. But what do we know? Is there anything missing here? I mean, I'll give you a clue. There is not something missing here. How do we know that it's not missing?
Type indices.
It's what?
Type indices.
Type indices. Yes. Somebody else? Couldn't hear? Louder? The type has to be equivalent. Yes, so the way I'd put it is that once I've matched on t-int here, this guy at the top, then I know that this A must be int in the rest of, everywhere from this closing paren to the right, A must be int, because otherwise it wouldn't have matched on this t-int. So in all of this, I know that A is int. So Y now started life with type TA, but now we know in this right-hand side that it's really t-int, and so I only need to match on that case. Yes, you had a question at the back?
I'm sure it's a typo, but your type signature is for the function foo.
Oh, yes, that I regret. I cannot blame on PowerPoint. These should both be foos as well. Thank you. Good. So, but does that make sense? So there's a sort of communication through the type variable, again, of the type signature, right? Type signature super important here. Communication through the type signature from one parameter to another. Do you see why this is actually just not very simple? Yeah? And why it might give you a bit of a headache. Right, and so these pattern matches are exhaustive, and again, you will send me mail if I complain about these guys. Anyone uncertain about why this program is actually fine, as is? That's okay. Yes?
What does DHT do with that right now?
Today, I think it actually does not, I think it doesn't report a pattern match fail. I'm not completely sure, because Sebastian is still in mid-flight. But I'm pretty sure that this is okay, actually. Somebody can try it and tell me later on. It does work. Good. Okay. Excellent. But it didn't used to work. And you can see that it's a somewhat sophisticated question to ask to be sure it's right. And yet it's so annoying if DHT doesn't get it right, because these pattern match warnings really support refactoring in a fundamental way, right? You want to say, if my program changes, if I change a data type so that the pattern match becomes non-exhaustive, please tell me I pay attention to those warnings. That's what supports refactoring. Okay, so that's good. Here's one more GADT case that's kind of a little bit weird. Here are two GADTs. And this one, this guy has a t-int, oh here, tint. This guy has a, oh no, this guy has a t-bool. This guy has a u-bool, right? So on bool they agree, but the t guy has a t-int variant, and the u guy has a u-char variant. So if I have something type ta to ua, so the a's must be the same. Now what? Okay, well the easy one is t-bool, yes, a equals bool, u-bool, so these agree, and then I can do something with the bools, and this time I'm just ORing them together. Okay. Now, are there any missing cases? Yes. T-int bottom. Yeah, what would happen if you get a t-int and bottom? Well, because that wouldn't, if you called it with t-int and bottom or t-int and error irk, then that would not match the first equation. So yes, you're absolutely right. You're saying there are equations missing, and I can show that by saying, suppose you call t-int f of t-int and bottom. Yeah. So and in fact here it is. Yes. And indeed this call is well typed. It's not rejected by the type checker because this has type t of int and this has type u of int, even though there is no u of int data constructor. And yet it's a bit annoying because I don't really need any pattern matches. So it's as if I've got to write something like this. But again, and in fact, this is actually, what's the word? This really could happen. Is this right-hand side inaccessible or not? It is not inaccessible. It is accessible. If I did make this call here, I would return true. Right? So this is actually a perfectly viable call. But when you look at it, you think, oh, if you just think of it in terms of combinations, you couldn't see a t-int u-char combination. That wouldn't fit, right? So, but as usual, bottoms are messing us up. Yes, at the back. Oh, yes. Can you do case analysis in the supposing you named this guy y, right? Then, and inside here, suppose you said case y. Well, would you have to put any cases in that case expression? After all, there are no values of y. U-char, no. U-bool, no. So if you did put case y in here, the obviously right thing to do would be to say case y of open curly bracket, close curly bracket. And yes, you can do that. You need to add the empty case extension that allows you to have empty case expressions. But yes, you can, and it's occasionally useful. Yeah. Does that then mean it's a strict pattern? So it does mean that that case expression is strict. So empty cases are strict. So yes, in Haskell, slightly weirdly, a case expression, case E of, if you just say X arrow blah, that is not strict in Haskell. If you say case E of, A cons A's arrow blah, that is strict because you've got to match the cons. Empty cases are strict. A little weird. I sometimes think that Haskell would be better if we just said all cases are strict, period, but it's a little late. You'd write to me if I changed that. Yeah.
Can you restrict the error to not generate the non-specific item?
Sorry, can you say louder?
Sure. Can you somehow restrict the error bottom to not accept the type of u of int? Let's say.
Oh, you mean could I arrange somehow not to make this not possible? To make it not possible to call error returning a uint, an uninhabited type. Yeah, I don't know any way to do that. But the thing is, there are inhabitants. One, a single inhabitant, the ubiquitous inhabitant, namely bottom. We haven't got into unlifted data types yet. We could go there. I think before long we'll be able to say data unlifted UA, and then we'll be good, right? But we haven't quite got to unlifted data types, and we're not going to do this talk. Yes? If you use a bang pattern here, oh, sorry, in this next slide here, if you said bang thing, then yes, then what would happen is the right-hand side would now be inaccessible. Because the only inhabitant of, you, anything else is bottom, bang patterns would evaluate it, so you'd never get to the right-hand side. Yes? Okay. Yes. Oh, I did say something about empty cases. Yes? Oh, when I said, so remember, bang patterns evaluate the thing. So if they're bottom, it'll diverge, right? So it's effectively bang patterns identify things that, just distinguish bottom from everything else. You know, a cons pattern distinguishes cons from everything else and bottom, but bang patterns just distinguish bottom. Yes?
This empty cases one you put up now, is that different only from case y of underscore in its strictness?
Yes. Yes, case y of underscore arrow blah is actually lazy in y, unfortunately, as I was saying. Yeah. Okay, fun. Oh, by the way, even just checking that this is okay requires another of those long-distance connections from what we know about y, remember? So long-distance stuff's important. Okay, now, how are we doing for time? Yes, but we're doing fine. This is good. We haven't finished. What about pattern synonyms? Hands up if you use pattern synonyms. Interesting, about a quarter, maybe a fifth. And do you love them passionately, or is it kind of just nice to have? No, some, Duncan loves them passionately. Okay, some passionate lovers, yes, well. I think they're pretty cool too, but they give us a lot of problems here. So this is a pattern synonym for cons list, for SNOC lists. So this is a pattern that matches against lists, but it splits the list into all the front part of the list and its last element. So you could think of SNOC as very like a data constructor in which the X is all of the list except the last element, and X is the last element. And we can write this pattern synonym by this view pattern, right? So it's like saying, as it were, whenever you see SNOC XX's, imagine replacing it by the view pattern. That's another way to think of it. And we reverse the list and then extract the X's part, okay? That's pattern synonyms, somewhat popular feature. Now, pattern synonyms, so now you might say, is this last? Is this exhaustive? It matches on the empty list and on SNOCs. So you might say, yes, that is exhaustive. But to know that, we have to reason about what the pattern synonyms do. And the pattern synonyms, because they're meant to be potentially quite complicated, you could do a lot of matching. So we give you a way to say what a complete set, I hope I got the syntax right here, I didn't check, what a complete set of data constructors is. So this says cons and nil, that's complete, that covers all cases. Also SNOC and nil covers all cases. And we like the pattern match checker to take advantage of that too. And there's no check, incidentally. You could declare this, and if you're wrong, right? So try to be right. We're not going to check that you're correct here, but we'll just believe you. It's like a pragma. Okay. Louder, please. Oh, well, is it an optimization? No, you don't need to put this pragma in for execution. This is just to generate pattern match warnings. Right, so here, if you don't put the pattern match in, it'll say, oh, there might be something that doesn't match these two equations. If you put the complete pragma in, it'll say, I can see, yeah, they're complete. We covered every case. Does that make sense? So it's more to do with static checking than runtime optimization. Yes? Oh, do pattern synonyms get inlined away? Absolutely they do, yes. So it's not an absolute promise. If you wrote 1,500 lines of code in this right-hand side, I'm not going to inline all of that. Or here I put in a call to reverse. If it was a call to a non-recursive function, so in principle I could inline it. So no, we don't blindly inline, everything. In fact, what actually happens in the implementation is for a pattern synonym, we make a builder which builds a value out of, builds a SNOC out of the pieces, and a matcher that takes a list apart and says whether it matches SNOC or not. Now, the matcher is just an ordinary function that's exported from the module defining the pattern synonym, and if that function is small, GHC will automatically inline it, and if it's not small, it won't. And I forget whether we let you put a inline pragma that says, even if it's not small, inline it anyway, but we should. Okay? That makes sense? So, but the way to think of it is pattern synonyms end up being very much like just ordinary functions. In fact, a pair of functions for building it and for matching against it. Yeah? Oh, that's right. This is oh, yes, thank you. This, I should have put an equal sign, put a left arrow here. This is a unidirectional thing. You can actually only use SNOC for pattern matching. You can make bidirectional pattern synonyms as well that let you both match and build. This one only lets you match, doesn't let you build. Thank you. I should fix that because that's just plain wrong as it stands. It'll be rejected because we can't reverse the thing on the right to turn it into a builder. Okay. So also good? Okay, so this is where we got to at this point. So I hope that you are about to run screaming from the room, right? We have reached the sequence. You remember the sequence of it looks easy and it turned out to be hard, right? That's where we're at. All these features, and each one of them is like little bit drops of snow that fall upon you, and gradually you're covered, right? And you're suffocating to death, right? If you're a compiler writer, it's really hard to deal with all of these interactions. And indeed, as an author, you have to, in principle, think about them all. They all occur in simple situations, and then you find a program which they're mixed up together, and things get hard. Okay? Yeah?
Do the arrows actually indicate interactions?
No, the arrows are purely, the arrows are not individually semantically significant. They are merely supposed to indicate a sort of plate of spaghetti, in which if you pull on any strand, the whole lot ends up in your lap. Okay? So, I mean, this is a serious problem because when you're building a compiler, you don't want a whole lot of ad hoc stuff. And we had a lot of ad hoc stuff. But then George Kariakoulis and his then advisor, Tom Shrivers, came and spent a week in Cambridge. And we had some sort of amazing, kind of wonderful insight stuff that led to this paper in 2015 that made me think, guys, problem solved. I was very proud of it. Here is the main figure, which, of course, I shall explain to you line by line. So what to say about this is that it really was a big step forward, but actually, even in the form presented in the paper, it was still quite tricky. The implementation was not straightforward and still has bugs, and it was slow. So we'd moved forward, but not far enough. If you nowadays, I think because of this talk, you'll be able to skip the details of the paper. But I think you might enjoy the paper itself anyway, because it describes quite a lot of the first part of the talk, but rather in a rather more systematic way. Okay. So, what to do? Things are tough. I know. Let's get an intern. So. This is Sebastian Graf, who's at Karlsruhe, doing a PhD at Karlsruhe, and he came and spent 3 months in Cambridge this summer. So it really is a talk about what I did this summer. And we spent a lot of time thinking, endlessly refactoring and pushing things around. So I'm about to take you, having shown you a vision of hell, I'm now about to take you by the hand, skipping, this stuff, take you by the hand and lead you to a simple and beautiful way to think about all of this that makes everything simple. Okay? So I hope that makes you feel happy, or at least happy in prospect. There are 2 ideas. Number 1, I'm going to take all of those features of GHC that I described and, as it were, desugar them into 3 very simple guards. I'll show you what that means. But I'm going to take all of these features and distill them into just 3, and moreover, they're 3 that do not interact. I can treat them in a nice, simple, orthogonal way. The second thing I'm going to do is to abstract. I've frequently talked about what values can inhabit a type. So I've got the idea of sets of values, and what sets of values does this equation match? So I'm going to show you how we can formalize that in a very straightforward way into a little data structure, if you like, or fact base. And by manipulating those fact bases, we can make everything simple. Okay? So 2 steps. Step 1, we're going to desugar pattern matching into guards. So here it is. So this is a slide to pause on, because I'd really like you to understand this. So here is a sort of some kind of random pattern with nested patterns. I haven't really talked about nested patterns very much. I should have, but I was taking it for granted. Nested patterns, a bang pattern, an as pattern, and a cons, and more than one equation. And I'm going to, as it were, desugar it like this. I'm going to say, I'm going to reformulate our equation as just a function applied to 2 variables, no pattern matching at all, and a bunch of guards. Now, when I've showed you guards before, even pattern guards, I only showed you 1, but you can comma them together to make multiple things. So what this says is, f of a's and y's is, the first guard is match a's against just t. If that succeeds, so if that fails, go to the second equation. If that succeeds, map t against x is v. That is never going to fail. We'll never get down here, but it might diverge, I suppose. Then bang x's. So this is a little funny guard. This doesn't quite exist in Haskell, but it is in this little intermediate language we're going to talk about. But imagine what this means is if you just evaluate x's. That's corresponding to this bang pattern at the top. Then, so notice I'm saying then. I'm sort of flattening out for you the process of pattern matching that is going on in your head. If I said what happens when you match against the first equation, you would say, first we match against the first argument, and that means first of that is match against just, and then match against the pair, right? I'm just flattening it out. So after I've evaluated x's, there's nothing further to do on the first. So now I'm going to match y against y cons w. Then I'm going to, I'll just define a local variable called b, which is equal to y bigger than 3. That's the right-hand side here. And then I'm going to match b against true. And if all of that succeeds, I finally get to the right-hand side. Yes?
Why was the b necessary?
Why is the b necessary? It's not strictly necessary, but except that in this little intermediate language, this, remember, is not source Haskell. This is my intermediate compiler language. It turns out to be much nicer to have, for the pattern matching form, to always have a variable here, not an arbitrary expression. Right? That, for example, means that if I match against t somewhere else, I can say, oh, I've already matched t against cons. Rather than if I've matched against y bigger than 3 somewhere else. So I'm just naming every expression that's involved. Yes. This isn't programmer stuff. This is entirely compiler internals. OK? Yeah. Does the order matter? Does the order matter? What do you think? Who thinks the order matters? Right. So good. You're all with me. It does matter because, well, partly, I can't possibly do this one until I've done this one, because I haven't got t yet. So in that sense, order matters. This bang x's, could I put that at the bottom? Would that make a difference? Yes. It would make a difference because, yes, I might. This, if I move that bang x's here to the, as it were, to later on, then I might fail to match against the cons for the y's, fall into the second branch, but x's would be bottom. I'd not evaluated it. So order is very important, yes. These are strictly ordered. There's a little bit of wiggle room, but not much. Maybe none. The lets can move around a bit. You could put this let. No, you couldn't put it earlier, but yeah, there's not much you can do here. Yes? Oh, in GHC today, does the order of, in Haskell, does the order of arguments matter? Absolutely it matters, yes. So if you flip the order of the arguments in a function, then provided you don't have any bottoms, nothing will change. But if you have bottoms, behavior can differ in small ways, because it depends on, if you give it bottom arguments, will it diverge or not? So yes. Oh, okay, yes. Yes, so in a call by value language, like ML, there's a whole new thing you could do, which is to say, could I match in a different order that somehow be more efficient? And there's lots of papers about efficient pattern matching. So one of the great virtues of Haskell is because of laziness, we can't do any of that. And so we don't have to. So this part is only concerned with pattern match warnings. Yes, hello, yes. How much what? Long distance patterns. I haven't shown you about long distance yet. Yes. I'm going to show you. So, okay, so this is how we do sugar, right? I've talked about all of this. Oh, I forgot to mention here, I've got f of y's here, but it was z's up here. But I can fix that up with a little let. Okay, yeah?
If I pass it correctly, it's a function that's like 2 arguments. The first argument is nested in the just. It doesn't seem to play any part in the function. So, okay, we're only evaluating it because excess is strict. Because I see excess playing no part in the final.
Oh, well, who knows? Right-hand side might mention x's. The question is, what role is x's playing? RHS1 might mention x's. It's an arbitrary expression. Right, yeah. So, all y's, all y, yeah, all the things, yeah. Okay, so the nice thing is this is the syntax for guards, right? Just these 3 things, bang x, a pattern match with variables, and a variable here, and lets. Remember, that was all I needed. Pattern match with variables and variable, a let with an arbitrary expression on the right, and bang. Those are the only three that I need, and I can take all of this stuff and desugar it into just these three. So thumbs up, that's the desugaring step. This only happens for doing pattern match warnings. I'm not going to execute this. This is just for generating warnings. OK, so now, now I'm going to take my function, and I'm going to turn it, therefore, into a bunch of, each equation of f turns into one of these list of guards. So each equation goes like this. Goes like this. So now my whole function looks like f of x and y is, and then a bunch of guards right-hand side right, or a bunch of guards right-hand side, OK? That's the way functions look now. Step 2, how are we going to check for, I'm going to just focus on missing equations, the ones at the bottom that you might worry about. I'm not going to speak at the moment about redundant equations or inaccessible ones, one thing at a time. So here's a way to think of it. You could imagine that I feed all values for the parameters in at the top. Then the first clause, by clause I mean one of these horizontal lines, the first clause will match some of those values and perhaps diverge on some of them, but some of them will fail to match or diverge and will fall out at the bottom. That set of values will be given to the clause 2. It will match on some and diverge on others, but some will fall out at the bottom, not covered. See what I mean? Think of these as sets of values. So clause 1 deals with some, clause 2 deals with some, clause 3 deals with some, and the question is this bottom set empty? That's the question before the house, OK? Now, what is this set of values? Well, it's sort of infinite, right? If I say, what are the set of values of type list of int? Well, there are a lot of them. The empty list, the list containing 1, the list containing 2, the list 1, 2, 3, and so forth. But what I want to do then is to represent sets of values in a finite way. And here's how I can do it. It's the stuff in orange. So this is something I'm going to represent in the compiler. And so this, I'm going to call it delta. Delta is a little data structure in the compiler that represents a set of values. And delta consists of, I've written it with square brackets here, some variables together with their types, vertical bar, and then some conditions, right? Now, this one says it's the set of values x of type maybe bool, where there's no conditions. What values can x take on if it's maybe bool? Well, it could be bottom, it could be nothing, it could be just bottom, it could be just true or just false. That's all, right? If it was a list, there'd be an infinite set. For this type, there's only a finite set of values, OK? But look at this one. This is a more interesting set. X is a type maybe bool, and nothing matches against x. So this is a sort of slices out a subset of values. And indeed, so nothing matches against x, so it can't be bottom, it must be nothing. There's only one value in that set. What about this delta? X is of type maybe bool, and just y of type bool is matched against x. Well, that set, since it's got this only the subset that matches against just, it could be just bottom, just true, or just false. And then, here then I could constrain y, and so I can have lots of conditions. So you should think of delta as being some variable types, that's the top level ones, the ones that I'm interested in, and then some conditions over those types, okay? Now I'm going to give you a concrete example. Here's a function f of just true. It desugars in the way that I've shown you to this sequence of guards. First match x against just y, and then match y against true. So now what set of values fails to match this equation? Okay, let me say it again. What set of values fails to match this equation? Well, let's try it. Look, initially I start with all values, and then I try matching against just y. Well, I could fail to match against just y. That's a possibility. So one possible set of values that could pop out the bottom not matched is the set of all x's of type maybe bool, where x is not just. I could say x is not just underscore, but I just mean x is not built with just. And x is not bottom, because if x was bottom, then this would diverge, and so it wouldn't fall out into the uncovered set, right? So these guys, this top line, represents the values that fail to match the first of these guards, the just. Okay, let me pause. This is very important. You got that? This is a description of a set of values that fails to match the just guard here. Anybody want to ask anything about that? Yeah. This is the unhandled cases for the first of those pattern matches. Yes. Yeah. Oh, can we compactly represent? You're talking about implementation. How do we represent these deltas? Very good question, right? But that's the compiler writer's problem. At the moment, I'm just talking about, can we even think about it, right? So at the moment, I just ask you how would we, in the compiler, how do we represent X is not just? Well, you might imagine a list of constructors that it isn't. It exactly is that. So this is pretty close to an implementation, but for now, we should just think about what's true and what's not. Yes? Are the conditions arbitrary? No. Well, you mean in the example? Oh, what things can appear here, perhaps you're saying. That's right. So I haven't actually given you the syntax of what these conditions can be, but they are, in fact, things like I can match, so very like a guard, actually, but this is one that isn't like a guard, X is not just, and here's one that isn't like a guard, X is not bottom, and there's only 3 or 4 of them. Very small number. You're going to see them all. Yeah, very limited number of guards. A very limited number of conditions can appear in this delta. Okay, so that's what happens if we fail to match the first just. But the other possibility is we might match the first just. Okay, so X is of type maybe bool, and X does match just, and in fact, I can get the value Y out of it. But then, how could I fail to match the second thing? Well, Y is not true and not bottom. And then I just take the union of these two sets. The union of these two sets describes all the values that can fail to match that equation. Crucial moment in this talk. That's the key idea, is that we take a description of a set of values and a clause, and we deduce a new set of values that fails to match the clause, a subset of the incoming set. Okay? Yeah.
The X equals the bottom in this case means that it cannot prove that X equals bottom.
The X is not equals bottom means this guy here means that the only thing that can fall out of into the next equation, if X was bottom, you could not get to the next equation because matching against just would already have diverged. So if you're thinking about the set of values that can be seen by the next clause, X equals bottom is not one of them. That's all it means. Just remember, sets of values. Say it every night as you get up. I mean, every morning as you get up, every night as you go to bed. This delta is just represents a set of values, and one thing you can say in a set of values, this value is not bottom. Yep.
This is, you say set, but it looks like the order would matter, so it would be a list.
Oh, the order does, or the order of the condition. No, the delta represents a set of values, but it is a finite representation of a set of values, and the finite representation is indeed ordered. Yes, because this Y only makes sense after you bound it here. Yes. But remember, it's the representation of a set, but it really is a set morally. Yes, yes. So we're going to have to go to warp speed now. So I just want to show you, look, I've shown you almost the whole thing now, right? So this is how you can think of. So I gave you some reasoning that said how you take a set and produce a smaller set. And here is the entire algorithm for computing the uncovered set for a guard. Look, for a list of guards. So you, given a delta and a list of guards, return a subset of delta which does not match any of those, which fails to match the guards. So how can we do that? For the empty list, if there are no guards, just return delta. If there's a guard that's a pattern match, then there are two things that can happen. Either we are going to, either X is not K and not bottom. I should have added not bottom here. Either one way to fail is to fail to match K, in which case I can extend delta by adding the extra condition X is not K. That's one way of falling through into the next equation. The other way is that I match all of the remaining guards under the extra information that X does match K. And that's exactly what I did here. That's precisely what I did here. That's the second bit, and that's the first bit. OK. And then it turns out that let is very simple, and bang turns out to also be very simple. So what I want you to get, the message I want you to get from this slide is, right, 4 lines of code, and I've gone from the desugared patterns to these deltas. So now, how do I go from the deltas finally? The question I want to ask about a delta is, I go clause, funny delta at the end. Now, if there are any equations that have been missing, then what I want to do is cough up a value of that type to show to the programmer. And if I can't cough one up, it's because delta is empty. So I need to find out a value of this set. I've got a representation of the set of values. Just produce one value. A small value would help the programmer to say, that's something that I haven't matched it. And it's actually quite easy. You just pick a disjunct from the union, start from x, and then pick a value that works for the conditions. So I'm going to do that by example. What about this one? If this was delta, so I pick the first element of the disjunct, and I'm going to say, pick a value of x that works for x is not just and x is not bottom. Guys, x is not just, x is not bottom? X is nothing. Seems pretty good, right? OK, so let's cough that up. Done for that. What about this set? This is a more complicated set. I start from here, pick a value of x that works for this. Well, just of something clearly works, and now I've got to find a value of y that works for the remaining guards. So I think you can see that by a sort of recursive process, I can cough up values, and I may end up saying there are no values. But in this case, I can say there are 2 values that fail to match, and this is a really helpful error message to give to the programmer. All right? So 3 steps then. Desugar, do the conversion into these deltas, and then given a delta, cough up a value or values that are in that delta to show to the programmer. OK. Right. So now, in the remaining 1 minute, how does this work for? So this really does scale to everything. I haven't talked about redundant and inaccessible equations. Works fine for that. Pattern synonyms works fine for that. Let's see, what's the word? The pattern synonyms, yes, I'm not going to say any more about that. GADTs works fine for that too. This just scales nicely but as well as having term equalities in delta, we have type equalities, and they work fine. So it's really nice that GADTs sort of turn out to be a special case rather than something new and weird. Long distance information, actually it's really easy. As we walk down those guards, we get a more and more augmented delta saying what we've matched. And then all we have to do is transport the delta that, as it were, popped out of this, and just transport it right to any nested case. So we just lift it out, and so that contains all the information that we know about enclosing pattern matches. It really couldn't be simpler. It's amazing. So this is really where I want to finish, just to say that we've sort of actually gone from, the looked easy, turned out to be hard, we thought some more, and it turned out to be easy after all. So thank you very much, and we'll take some more questions. Yeah, Duncan.
So I presume you're totally confident about this type of solver.
I'm totally confident about that it will work.
That this works, and so therefore we are totally okay to rely on this as a theorem prover.
Well, remember that it will. Remember that thing about greater than or equal to and less than or equal to. So there's 2 caveats. One is, by having more complicated guards, you can put real computation in there that we're not going to reason about. Second thing, when I said it can go exponential on you, because people really hate it if the compiler just says, and you have to go and have coffee, there's a sort of throttling mechanism that says, if we have too many disjuncts, remember those unions? If you get 2 to the n things in the union, right, that's bad. So we sort of throttle it to say we're never going to have a union of too many. And that means we may err, but we try to err in a conservative direction that might over-report. So we try to always over-report failure. So we may say, look, I can't prove that these equations are exhaustive, and I'm going to tell you, rather than I can't prove that they're the opposite. I mean, so in other words, if it says it's exhaustive, it really is. That's the thing you want to know, including for these computations.
I'm afraid we don't have any more time for questions.
Right.
But will you be around in the break?
Yeah, I'm around the entire day. Yes,
Fantastic.
So I'd love to talk about any more of this.
questions during break?
So enjoy your coffee.
Thank you
And
so
we had
much.
lots of questions too. Thank you.